So the conclusion of the first part will be rephrased as a dream, which is, I don't know, different people have different dreams, which is, so you want to like patch these local universal families together and get some universal family over some moduli space. So patch together local deformations, or patch together these local deformations to obtain a compact moduli space of Calabi-Yau varieties of a given type. Patch. Oh yeah, patch. Okay, I think. And then you want to get some compact moduli space with some universal family. And so if n is equal to 1, dimension is 1, this is classical, this is the moduli space of elliptic curves. There are also variations to this. If you want your elliptic curve to have some level structure, you also have universal. You have moduli spaces of elliptic curves with level structure and universal families above them. It works for like principally polarized surfaces as varieties. If n is 2, so in a moduli space of K free surfaces, so this means, we want this to have a modular interpretation, right? We don't. We don't just want to compactify, we really want that the strata we add have some modular interpretations as the generations of Calabi-Yau varieties. So for n equals 2, this is forever upcoming work. So this always appears at the end of the year, every year. By Grossack and Kiel-Siebert. So the way this works is that every now and then there's like a new push to finish this paper, and then so one of them will give some talks and they'll be like, okay, this is going to appear at the end of the year, and then nothing happens. Another few years later. But I think there's a draft, and this uses mirror symmetry and canonical coordinates, which I'll say a bit what they are. Canonical coordinates. And then of course, if n is greater than 3, this is y. So those are not, these are not things I'm interested in. This is not what this lecture series is about, but it's kind of useful to keep this kind of on the way. Questions, comments? All right. So okay, now we're going to get into towards enumerative geometry, and also there will be some that's usually the reaction. All right. So we want to study. So next we want to study study periods around 1 points. Let me introduce this. So what they will be, so you have this, I'm going to use the word B, you have some small disk, you have this family, maybe I put it here, you have some information, and then we want to define some maps, so periods which are multi-valued locally holomorphic maps which associate which take B which go from given by T mapping to integral of omega T over some cycles. So L are some cycles in Hn. Of X, T, and then this is the holomorphic volume form. Holomorphic volume. So it's a 1-0 form. So this is where we're going towards. One way you can think about the interest to do this is you might want to study the variation of the complex structure around Mont points. So this is, it helps you to study variation of complex of C structure around Mont points. When I say they're multi-valued, it means that if you go around the origin, you may come back picking up some like contributions like log of something. So I'll make some comments about this. And the first step when we want to do this is we want to have some good coordinates. So now also make some comments, which is so this is the holomorphic volume form, and we want it to be normalized such that if you integrate over some SYZ fiber, you want to get 1. So this is SYZ fiber. It should be isomorphic to S1 to EM. We'll get a little bit towards this later, what I mean by this, but yeah, so I just want to, maybe everyone knows what I mean by this. So imagine if you have inside, so if you have some sub, if you have some sub manifold which is S1 to the n, then you can imagine that you can integrate. You can imagine that this is the integral of over S1 to the n of like d of the product of the dxi divided by xi, and that thing really is. That really gives you 2 pi I to the n. Yeah? But maybe the existence of such fibers is just maybe just existence of these will be guaranteed by intrinsic merit by IMS, guaranteed by IMS. So what I mean is, if you want to know whether you have these, you could either talk to someone at IMS and they will tell you why you have some, or you could, they're guaranteed by the intrinsic merit. But I'm being deliberately vague because I don't want to spend too much time.
It doesn't, I mean, it's this class that's a guarantee, but the new MVN property of the property is
yeah.
is supposed to be the same.
Absolutely. Yeah, excellent point. Thank you. Alternatively, so F is the like deepest vanishing cycle. What's the word? Not deepest. F is alternative existence. Garrel of F. Guaranteed by the one property, which is that, so every time you go around, a cycle is being sent to like itself plus some vanishing cycle, and then there's like I told you, there's the stratifications, and so the deepest one is this. So we want to, so we have this holomorphic Gordon problem, we want to normalize it in this way. And then we also want to get some coordinates. So recall that locally the moduli space has dimension hn minus 1, 1. Right? So the dimension of the moduli space, so private, where it's hn minus 1, 1. So this means that we should have a basis of n of that many. We should have that many local coordinates, so we could find some explicit basis, and so that's what we want to do. So we want to find the explicit basis, which is going to be, so find coordinates, local coordinates. So we want to have, want local coordinates, or we can get local coordinates by mapping by taking So if you so this is a map. So if you so let me write some gamma j in Hn xt. Let me rephrase it. So if you have, we can always do, we always have this map, yeah? and that can give us a reparameterization. Oh, yeah. Thank you. And so we want, so this gives us a map where here we go from B, or maybe B away from 0. And then this is going to be inside some disk to the hn minus 1. So we can always do this, and we want to get some coordinates where so this means we want to choose with the gamma j should be a basis of h n minus 1, 1 x t or z. Now, before you complain, so this supposedly dual to h n minus 1, sorry, h n minus 1, 1 x t z. So I'm a bit on slippery territory here. So we have well-defined Hodge classes in h n minus 1, 1. Yeah. We know that we expect the dimension of our moduli space to be the dimension of this. Now, moreover, we know that the Kodaira-Spencer map takes goes from the tangent space here to this moduli space to this cohomology group, this Cauchy group. So it is not like crazy to expect that there are some dual, there's like a basis which is dual to a basis here. Now, a basis of cycles of some cohomology group, which I'm not defining, such that when you do this gives you an isomorphism. I know it's a bit of vague, I'm being a little bit vague because I don't want to spend too much time on this, but this is kind of reasonable expectation, and you can make this precise. Yeah? Yeah, that's right. So absolutely. So you can, you know that you're going to have this, right? What Pierre is saying is you can look at the monodromy acting, and then that gives you a stratification, this filtration of homology classes, and then one of these will give you coordinates, which is essentially what we're doing here. The reason I'm stating this way is I want you intuitively to think about these being some sort of quasi-dual classes to the elements that characterize local deformations. So,
say again, do you have a definition of n-1 of z?
Not really, yeah. So, sorry, let me say the definition is the following. So, you know that monodromy does something to your, so if you have some cycles, some n cycles, and if you apply monodromy, you can like stratify this. Yeah? And then there's going to be one group that you can use for coordinates, like in this way. And that's the one I wanted. That would be a definition.
Is it just like kernel of t squared divided kernel of t?
Fantastic. So let me use this definition. So the kernel of t.
Like t minus like n squared.
So I use ti. There was some mi squared as a map from Hn xt z to our Hn. Yeah. Okay.
The omega t was like the kernel of t minus I is the quotient.
Yeah.
But then I don't know if it's gamma j, are they really like well defined, or are they defined up to a multiple of f?
So they will be defined up to a multiple of f, but that's okay because if I have some multiple.
Oh yeah, that's what. So you should not change this coordinate.
Exactly. Yeah. So there will be. So this is. So maybe I need to portion up by something, but this is well defined up to well, z times f. But that's okay because if I add here plus mz plus the integral of over f m omega t, that still gives me the same linear. Sorry, when you go around, you get this with some 2 pi I here, or e to pi. So one can make this precise, and maybe this is the definition. I didn't want to like spend too much time on this because I want to instead tell you when you have a good basis of coordinates, and then I'm going to give you a slope. Yeah. So apologies for being a bit imprecise. So now, yeah. So I think you will see in a second why I'm not spending too much time on this. So coordinate, which we're going to think about. So we're going to map. We're going to look at one parameter subfamily. X0. And then we're going to take, so coordinate is canonical if, so Q maybe to some K, maybe there's like some extra number here, is equal to the x of the period integral 1 divided by 2 pi I n minus 1 So there's always, I'm going to make a lot of mistakes where I take 2 pi I to the wrong power. And so eventually I'm just going to set 2 pi I to be 1. And then at some point I will make a mistake with plus or minus 1. So at that point I will also set minus 1 to be 1. Yeah, so where we have this, yeah. And then we have some gamma in h n. Well, in this case it would be this hn minus 1. And so this means that monodromy, so this is, we have, so the monodromy is that this expression 1 over 2 pi I to the n minus 1 gamma cube, you go once around 0, you get the same thing plus some multiple minus 1 cube plus some multiple of 2 pi I k, 2 pi I plus logs. So let me maybe put it out. So I'm making a I'm making a definition of what it means to have a good coordinate, and it means that, well, you can express it as exponential of this period integral, and it means that the monodromy is really well behaved. Now, if I just give you this like this, if I just throw this at you, you might think, what's going on, what's the point? Well, let me give you some example that will illustrate that this is actually that this is not something you will automatically obtain. Oops. And then the slogan will be that it would be really nice to always have these canonical coordinates without working too much. Okay, so we do some examples that hopefully will illustrate what we're talking about. So example. So if I have an elliptic curve, so we have our moduli space of elliptic curves. Can be identified, we take the upper half space minus the origin, we quotient by SL2Z, and you add some cusps. And so this is what it looks like. Now the mum point is at infinity. The mum point, and the 5 over the mum point is corresponds to nodal elliptic curve. So nodal elliptic curve. Whereas the other point, I mean, maybe this point here corresponds to some smooth elliptic curves. Okay, so what did I write here? So we have the upper half space, the upper half plane, minus the origin. We quotient out by the SL2 action. We get something that looks like this. We add some cusp points. Let's ignore what that means. And then we have this mum point at infinity, at I times infinity, that corresponds to nodal elliptic curve. We can write this. We can write very explicitly this family. This is what I want to do now. This family here, we can write very explicitly as follows. This is the tape curve. So we have the tape curve. So this is given by star quotient out by q to the z. So in this quotient we have an action where the action sends z to z times q to the d. So fix some d. So we fix some d, integer d. Now we have a map down to a disk. In this case, this is really the elements in Z, such that the absolute value of Z is between 0 and 1, but not equals to 1 and not the origin. And then we have an isomorphism of a fiber, which is given by, so this is so if I take C and I quotient out by the lattice generated by 1 and 1 over 2 pi I log Q, then I have a map that goes from here to here, which sends Z to Z, e to the 2 pi I Z. This is well defined. 1 goes to 1. Yeah. And then this one goes to q to the. Sorry, this one goes to plug this in. This one goes to q, which is equal to 0. So 1 is equal to 0 and q is equal to 0. So that's all good. This one is an elliptic curve, right? So this is like elliptic curve. Okay. And then here is an element indicator. So this is a so-called take family, and then you can compactify it by adding a point.
This is not that. You just fix the Q.
That's right.
It's not like that.
Yeah. So this was just an isomorphism.
That's not.
This one?
Fix the Q.
Yeah, you're right. You're right. That's right. That's right. So you fix a Q, and then yeah, you're right. You're right. We have a map. Yeah. Well, you fix a Q, and as you vary Q, you get a map. Yeah. So you get yes. You're absolutely right. Sorry. So we get a map like this, where this one is just that Z, and then here. So this is. Yeah, so this gives us this family, and I guess here maybe I should call this Q. Okay. And now we want to like compactify this over 0, and so we can do this. So add in x0, which is so this is x cubed, x0, which is cycle of d lines. Cycle of d lines. So there's a way of like constructing this family properly. So I'm just describing you the features. So this gives us. So this is a. So that family is a.
So for each D, you can choose this.
Yes, absolutely. You can, yeah. So here, if we take d equals 1, we get the universal family over that moduli space around the norm point. So M1 bar, M1 bar. So we get this with q equals 0. So q equals 0 here is the nodal. This is the nodal. canonical. Those are canonical coordinates. So that's the statement is these are canonical coordinates. So Q is a canonical coordinate. Yeah. What does this mean? So I told you it means we need to have some cycle. So your elliptic curve, you need to take a cycle which is known in H1, and the claim is as you go around 0, if you take that integral and you go around 0, you're just going to like send Q to Q plus you're going to send Q to Q as you go around. Now, okay, so I see confused looks. So let me do it the other way, where we don't get canonical coordinates, and then that will hopefully be helpful. Yeah. So that's an example of a canonical coordinate. You can think about what's the cycle in H1, and you can like play around with this definition. But now let me tell you the bad, not the bad, the other example, where we don't have canonical coordinates, and hopefully this will convince you that it's nice to have canonical coordinates. Okay, so now we do another example, which is so that was this is the universal family. This is the universal family. Universal family around 1 point. It's an example we don't have canonical coordinates. Maybe, yeah, I wrote down that the price that you have to pay is, so the price you work in analytic coordinates. And it depends, you may consider this to be a price to pay, and you may consider this to be a feature. Or you might be much happier. So let's do another example, which is example of non-canonical coordinates. So it depends on non-canonical coordinates. They are pencil coordinates. So we take a family of elliptic curves, and this will also become relevant later. X, Y, Z minus T cubed X cubed plus Y cubed plus Z cubed equals 0. So this is inside, we take P2 portion out by mu3 times M, where M is the following. So this is just a fiber. Yeah. So M is, we take C minus 0, union 1/3 root of unity, and then portion out by U3. So this example is it shows up at several places in the literature. There's like there's a paper by Macri. There's a paper by Pierrick. Also, at least two papers. Then I think it also shows up in the paper by Pierrick, Lorenting, Schreckray, and Honglu. So it has like a long history. So et al. And it is the modalized space of elliptic curves with the gamma 1 3-letter structure. So this is the M is the modalized space of elliptic curves. Gamma 1 3 structure. this is space of pairs.
So when you say ET3, that is a reversal from the
That's right. Yeah, I should write it. Yeah, I should write it this way. So yeah, this is the universal family, and then this is yeah. Let's just write it. This is universal family. Universal family. Absolutely, thank you. Yeah. So this is the sort of very nice setup that we like.
Okay, let's see what is the accuracy. This is not unit, what 1/3 of mu.
That's right. So mu3 are roots of unity. Sorry. So it's 1 and e to the 2 pi I plus minus divided by 3. Roots of unity.
That is also C.
Sorry?
That is also C.
That's correct. Yeah.
But then you see
Oh, sorry. Yeah, absolutely. So set minus these 2 points. Yeah, apologies. Yeah, fantastic. Yeah, thank you. So let me explain this. So if you set in C equals 0, it's a union of coordinate axes. So that will be the Mont point. If you take t cubed to be a third root of unity, then you get a nodal elliptic curve. So maybe it's worth to draw it. So over 0 you would have a cycle, and then we have these like 3 normal ones. So the 0, so it's 0. This one is 1/3. We have another one. And then over the other points you have a smooth. The reason I write this is, and then you also have, so if you just put some t here, you would figure out that there's a, so 2 different t's such that their cube is equal, so 2 different t's that differ by root of unity give you this isomorphic elliptic curves. That's why it's a convenient description of writing it this way. Yeah, so we would just that. So there's like a base change. So that's the universal t cubed here. Yeah? Makes sense? Yeah, very good. Other questions, comments? Yeah.
So you add the point of unity that you will hardly say
That's right. Well, it's not too bad. So here I think so I didn't forget you right. So at infinity we have a cycle of I think 9 lines. 1, 2, 3, 4, 5. Sorry.
all together in 1/12, right? So this is already 3.
Sorry, 3.
What is the question?
Yeah.
You want to get E1 resources.
That's right. Yeah.
This will account for 2.
Okay. Yeah. Okay. So yeah, you're way too ahead of me. So what's a fiber over infinity? And you have to count all the characteristics. It has to be 12. So you're saying that you have to do a complicated calculation. Yeah.
I mean, like if you have mystery, it's actually there is some orbital points. Actually, there is no other sigma fiber.
Yeah. That's right. Sorry. Good point.
It's like once you get rid of the mystery, there will be 3 nodal ones in the cycle of time, which give you 12.
That's right.
But here, because the quotient of this mu3, you don't see really the 12. Only one.
So even the infinite one is orbital one.
Yeah, that's what it's.
Yeah. Thank you. Apologies. Yeah, of course. More comments? Right. So now we can do so let's get canonical coordinates. Let's find canonical coordinates, and you'll see that this is non-trivial. So goal. Let's use it. Call it get canonical coordinates. Goal. Get canonical coordinates. And the reason I'm doing this example is I really, well, first of all, it's going to come back later, but also I really want to emphasize that canonical coordinates is a bit of a, it's annoying if you don't have canonical coordinates. All right, so if t, so first I'm going to take, first I'm going to restrict just to c star squared, because I can. And then the equation is t cubed x plus y plus 1 over x y equals 1. This is something you will have seen before. It's the mirrors of the potential of 2q2. Then I will go even further, which is that inside here I have a positive real locus. So I can look at the solutions of this inside the pot. Like I can even go further down, which is I can look at, assuming t cubed is positive, I can intersect this with the positive real numbers. Where here, I really mean, C star. This is C star. I look at the positive real axis, and that also has a solution, and then we call this gamma t cubed, and then we draw it from it. So how do you draw this? Well, you take Mathematica, you draw it, or you get something like this. So this is gamma. And really good time to use colors. Let me try again. Colors. More or less. And in particular, what you find is if you vary t cubed, you fiber, pencil out, or you know what the right word is. Pencil of. What's the word for this? You have a you span all of positive square. Yeah. So you can span. There's like this kind of singular point here, and then you span everything. And for in the limit, you have the limit, so the limit where t goes to 0, gamma t cubed, you get the cycle through that. So here, and then the number. I mean, you don't see it here, but you get the cycle.
You mean it's like a foliation?
Foliation is the word. Thank you. Thank you. Foliation of, yeah, absolutely. Foliation. Thank you. Okay, so this works because of the special shape of our coordinates. But then we also have another cycle, which is the SYZ fiber, which I'm just going to draw like this. Yeah, you can imagine your elliptic curve. Right? So if this is the plane, this is R2. So we're kind of limiting to. Yeah. Then you have this cycle, but then you also have some other cycles somewhere else, right? But also, and you have this SYZ fiber. So this is going to be this beta t cubed, which is the SYZ fiber. I'm always jealous of topologists and algebra geometrists because they can just they can draw these cool pictures that now I can pretend. Okay, and also the SYZ fiber has the property that if you take the limit t cubed goes to zero, that still is of beta t cubed, you still have the same one. There's no like, it doesn't like shrink or whatever. I mean, which is expected, right? So then let me draw a picture again. So we have, so this is the t plane over 0. Now I'm going to try to draw an elliptic curve, and then over 0 it becomes like this. And the way we're going to draw our elliptic curve is we have this cycle here, and then we have this. So SYZ partition, yeah, makes sense. And then as you degenerate, you get here, and then these points become, I think this is the picture. So that one is gamma 2, and this one is beta. Okay. Now you can compute that. So the monodromy sends gamma t cubed to gamma t cubed plus 3 times. And it sends this one just to itself. So you can see if you take monodromy minus identity, this is a vanishing cycle. So this implies vanishing cycle. So I guess maybe that was the lowest vanishing cycle. Is right. The one where you square it. Anyways, questions? So now let's compute. So I told you we're interested in coordinates, we're interested in these integrals. So let's compute them. And now that's where it's going to get nasty. So if we integrate over the SYZ fiber, it will be 1 divided by 2 pi I. So remember, in the canonical case, that should just be 1. But no such luck. This is 1 plus some d bigger than 1, 3d ddd, t to the 3d. So what I did, I can just define using as a residue. I take some residue of, I take the standard 2 form on P2 or portion, and then I take the residue of this one where the bottom is a defining equation. I mean, just something standard. That's nothing much. And then I get this, like, first of all, I get this, like, not so nice expression. That's only values. So step 1. So step 1, we replace to the right. We change this to become the one we had divided by this expression. This is fine because as a power series, this starts with 1, so you can invert it. So that's the first step. And we can always do this. So the holomorphic volume form are one-dimensional, but as the sections of the holomorphic volume of H n, 0 is one-dimensional. However, you can always modify by some holomorphic function, which is what we're doing here. Right? So this is modified by holomorphic function. Yeah. So this is already annoying. It is either annoying or pretty, depends on your taste. All right. So now then, let's integrate that cycle, gamma t cubed omega t cubed with the new form, and maybe I should write 1 over 2 pi I, but maybe I'm just stopping to write this. And so you can compute that this is equal to log of t cubed plus some complicated expression 5t plus I just wrote down the few terms 3 divided by 2t to the, this is a t cubed, this is a t to the 6 plus blah blah blah. Yeah, well, if those were canonical coordinates, we would have to just get log of t cubed. So we want to solve this. We want to write equals log of maybe q to the cube, because we have gamma. And we want to solve. And then this implies that our q, which is q of t, is like t minus 5 t to the 4 plus 32 7 minus blah blah blah, etc. Okay, so now and then q cubed is a canonical coordinate. So this is, maybe they rewrite it here. Yellow is the color. So having done all of this, we obtain that q cubed is a canonical coordinate, which means that q cubed is equal to the exponential of integral of gamma. Okay. So this is an illustration of finding canonical coordinates is cumbersome. So let me. So there are two possible interpretations. You could say that, well, you find these beautiful homomorphic functions that have some interesting meaning, or you could find it a bit annoying. Yeah. So so if you care about canonical coordinates, this is a bit annoying. So recap. So normalize. Normalize f omega equals 1. That's step 1. Step 2 is find, this is XYZ fiber, or the one with the monotony as described earlier, or canonical coordinates qi, exponential of the integral over some cycle, gamma I, omega q. So the gamma I is good. Okay. Now, so some basics. So why do we do this? So reason number 1, if you're interested in constructing moduli spaces, you really need this. It would be very hard. It would be very hard to construct these compactifications to moduli spaces with universal families if you didn't have canonical coordinates. That's one reason. But there's also another reason, which brings me to the next part of like a great strength of IMS. So note that so gamma I is fibered in S1 to the n minus 1 over a curve over. I'm going to start using some nasty words, tropical curve. And when I say note, there's no like way you can deduce this, but I'm just claiming. My claim is that the cycle, like the real locus, suppose the real locus gives you a so-called tropical curve. And then you can formulate a hope, which is that you can find bases or basis of H. I'm gonna now call it n minus kk in analogy of what we did before. Apologies for being a bit vague, such that let's call this basis, I don't know, L, such that if we have an L in here, such that L is fibered in k cycles, in S1 n minus k over tropical k cycle. Again, I'm not telling you what this means, and I probably couldn't tell you a general definition. One way this becomes interesting is, so this is another, like, and you would expect that L is Lagrangian, and it corresponds to some interesting element on the mirror side in the derived category. It corresponds to some interesting element, some interesting sheaf, F, in the core of the mirror. Now, I'm just throwing this at you without any explanation, but this is not crazy, because there are papers where there is an explicit correspondence between Lagrangians on one side and elements like sheaves supported on subvarieties on the other side, and I want at this point mention papers by, so there's one paper by Chan, Mariano, Lau, there's a paper by Ross and Matesi, and more papers. And this is also something that we will like see when we get to the more like Gen Z part of my lecture series. I just I haven't told you what the symmetry is, etc. But it's not a crazy hope.
What is if this hope can be achieved, what is an outcome?
Absolutely. Thank you for asking. Let me tell you the outcome. So the outcome. So I'm gonna just pretend I know what mirror symmetry is, and I have a mirror too. So L is in X, and this is a mirror. So the outcome would be that on one side, you're integrating over these L's. We usually put that integral on the B side, so don't put it here. So we're going to integrate over L, this homomorphic volume form, Q. And then that should be correspond or even be equal. I'm going to write equal to a component of the J function, which is going to be determined by the mirror object F. So I'm going to claim that F is, I'm going to put it this way, support of F of J function. So this is a J function of X. This is J function, which is a generating function of J. 0, the origin of x. Yeah, absolutely, thank you. Yeah. That is all. And there's even more, I mean, and even we would expect that we have support of F, we tropicalize it, so some trop support of F, and then you can, I don't know, and then the cycle here will be fibered in S1 to the n-1 over this tropical cycle. So this would give a very like satisfying way of doing homological mirror symmetry. In the sense that you have this kind of this like explicit SYZ correspondence. Yeah, and not just that, but you'd also have an equality between some enumerative information and some period integrals. And let me tell you why this is not crazy. So evidence. Well, I equals j, or j equals I in canonical coordinates. So I is the we'll maybe say something about this. So this is the collection of period integrals. Indexed by some cohomology classes, and then this is the collection. This is really the sum of these J support F X check with dual. I mean, so when I write this, I have to be careful because I need to choose a basis and a dual basis and everything. But the claim is that you can write the J function, which is this function that contains a lot of enumerative information. You can like decompose it component by component, and then you want to match it with the I function, which is the collection of these period integrals on the other side, component by component. And so you kind of want to like say which components correspond to which, and somehow this correspondence is a very like satisfying way of associating. There's also other things you can do, which maybe I'll just mention, and then we don't. So since you're in Sheffield, you could ask about like the moduli space of B brain. Now this is very speculative. B brains, of corresponding to F. Like you fix some chunk factors, you specific condition, you look at the moduli space of these. Then you want to like have a correspondence with the moduli space of A brains. So here you put class L, and here you put class F. Okay. And then you could like expect to have something like this, and then you could compute some invariants in cases where you can do this. So this, so there's like, you can formulate such conjectures, and check them in examples.
So if you say yes, that Hamilton branches, you don't have something from that.
Yeah, I have nothing. Yeah, I'm just being delusional. Yeah, so I'm not. Yeah, so this is. I have nothing. Yeah, I only have examples. So like the best claim I can make is if you look at these papers and you apply it to toric Calabi-Yau threefolds, which is the case I consider, then it matches. Yeah. Yeah. So the reason I'm mentioning this way is like, so it's really key to have canonical coordinates.
When in your story you will have some maybe alignment.
One more time?
Yeah, if you write the initial form, when you are interested in algebra geometry, there will be a line model which gives class of this.
That's right. Absolutely. Yeah. Thank you. Yeah. So then, yeah, absolutely. So yeah, you need to choose a line bundle, and then if you do it in the if you do this, if you do the cases that we'll be looking at, which is let's say, I'm just going to P2E is going to correspond to something, well, to the mirror family, which we've actually already seen. Then you need to, anyways, you need to make choices, but you can always, there's always like a, to rephrase the question is you have to choose the right line bundle that will correspond to the right family junction. So there's like some matchings to do. And I want to emphasize that this is not this is a kind of a intuition that you can then go to examples and check. It's not the like good luck trying to do things like this. And to do this, so to have such a diagram, you really need canonical coordinates, but also to have this sort of correspondence. To have this sort of correspondence that I've written here, that also you really also need canonical coordinates. Yeah. And so now is maybe my last claim, which is, yeah, let me just so. Let me finish by some claims. So the first remark, so universal or deformations. So they're constructed. So there's a sequence of papers. In that setting, there's a paper by Siebert. There's a paper by IMS. So Conan, Zeeman, and maybe there's some like extensions to this. There's also a paper by Godard, Philippe, Felton, in opposite alphabetical order. There's a recent work by Godard and Corti in the Farmer settings. Corti. And there's like a lot, actually there are many more papers. And then, so the key why I emphasize these things is Siebert families or intrinsic families, so GS/IMS families are in canonical coordinates. And that really solves a lot of headaches. And so the like one outcome of this lecture series will be to prove that statement. We will prove that statement using no calculation. So we'll prove. We'll see a proof of J equals M with no calculation. So really, as you have a period integral, you have a cycle, you integrate over a cycle, in that case those will be Lefschetz fingers. And that expression, it will be an expression like this. So cycle, you integrate the whole over some cycle. That's exactly going to be equal to a term of the J function, or even all terms of the J function. And so that's kind of the motivation behind this. So the reason as an enumerative geometer, as a traditional, so as an enumerative geometer, you like canonical coordinates because you can phrase things like this, and I think proving the statements that I will show you, you can do by other methods, but they always involve calculations. If you are in a very general setup, you want to like get rid of calculations. Yeah, maybe I probably went over time, so yeah, maybe that's a natural. I plan to talk a lot more, but it's always takes longer. So maybe that's a good place to start. To finish.
More questions?
I'd also be very happy, like, you can tell me that this expectation is completely wrong. I mean, I'd be very happy to hear this. It could be, but I think it's been something that you just doing examples, yes?
I don't know much about this, but is there anything you can say about heterogeneous invariants?
Oh, excellent question. So that's outside, basically heterogeneous invariants are outside of this framework, at least for now. You can compute them by mere symmetry, but it does really use some like BCOB machinery, which is very intensive, and I cannot tell you how this fits into this framework as of now. Yeah. I mean, one can say a lot about it, I cannot tell you something new about it. But that's of course it. So something there are papers on this. Some like you.